So in this tutorial we are going to learn about multi-stage interconnection network. So here you have an example of a multi-stage interconnection network. It's called delta network. But before diving deeper, let's just look at the statements. The delta interconnection network is a digit controlled multi-stage interconnection network made up with Banyan switches. And uh, so Banyan switches are also an important part of this multi-stage interconnection network design. At the same time, I believe that this stage thing needs a little bit of attention. So let we do a quick recap of our previous day study. For that, at first, let we go to the Banyan switch submodule. So, what is a Banyan switch? A 2x2 Banyan switch has two inputs numbered 0 and 1, and two outputs are there 0 and 1. Outputs are also numbered by 0 and 1. Now some properties go like the Banyan switch has a switching control built into the switch itself. That means controller has been implemented into the switch itself. Now every information unit that comes into the Banyan switch has a header that contains a bit indicating its destination, and the meaning is something like, say, information arrives into the Banyan switch. Now the information has to go out of the switch by following either of these two paths. Now the question is which path to follow. This header will contain the information of its destination. Now if the switch reads the bit and it has a value 0, that means header or first bit of the header is 0, then the output will be directed towards the output line numbered 0, and if there is 1, into the header, that means first bit of the packet, then the output will be directed to the line numbered 1. So by connecting these Banyan switches, actually the so-called single stage and multi-stage interconnection networks are built. If you can recall the shuffle exchange network that we have studied during our previous day discussion, yes, here it is. You can see that this shuffle exchange network has been implemented by using 4 Banyan switches. Now, what is the stage here? If you carefully analyze the diagram, you can find that the processors are connected among themselves by a number of banyan switches. Now, this number of banyan switches actually for a stage, as between the processors there is only a single layer of banyan switches. Hence, this is a single stage interconnection network. Now, uh, let me move to our discussion for the day. That means multi-stage interconnection network. So we have started our discussion with delta interconnection network. So I should zoom it out so that the entire thing is visible onto the screen. Yes. Now this is an 8 by 8 delta network. So why 8 by 8? Because 8 processors are connected to 8 processors. Now each rectangle, purple rectangle, represents a 2 by 2 banyan switch. Now why this is multi-stage interconnection network? The justification is that you can see that here we have 3 layers of switches. This is your layer 1 or stage 1. This is your layer 2. This is your layer 3. So because of this different stages involved here, this interconnection network or this type of interconnection network is called a multi-stage interconnection network. Here this is basically a generalized view of that. Now let me look at some of the example networks that which are in existence actually. This multi-stage interconnection network is called Omega network. So now how you can build the Omega network? To find that, first jot down the number of processors. So just write it. Say n is the number of processors. In our example, the number of processors is 8. So let me write it down. So yes, and n number of processor or 8 number of processors has been numbered from 0 to 7, and into the green rectangles they have been numbered using decimal numbers, and on the left of the decimal numbers you can see their equivalent binary representations. Now onto the right side, extreme right side, we have the same 8 processors. Now you have to find out the interconnection network root, or in simple words, which processor will be connected to which switch, and which switch or which output port of the switch will be connected to another switch or processor. So first, uh, just look at the statement. The omega network is basically is a delta network, and uh, number of stages. How many stages will be there? You can find it using this formula, log n base 2. So how to apply that? Let number of stages for our example will go like what's going on here? So let's get it right here. I'm not going to, okay, write it here. Number of stages will be just a moment. Let me make it correct. I don't know what's going on. I should use this text process. Just leave it. Let me draw and do this side. The number of stages you can find using the formula log n base 2, where n is the total number of processors into your system. Hence, it is going to be 8 in our case, and base 2 equals to log 2 to the power 3 base 2, which is equal to 3. So, for this example, number of stages will be 3. You can see that here we have 3 stages drawn. Now, next you have to find the number of switches into each stage. The answer is simple, n by 2. That means for 8 processors, you will have 8 outward edges, right? Now to 8 outward edges, you actually need n by 2. That means 8 over 2 number of switches, that means 4 switches, as each switch has 2 input and 2 output ports. So if you combine all the inputs of the switches, you will have 8 inward edges to connect the 8 outward edges of the processors. So next question is, which processor is going to be connected with which port of the switch? That is a big question, and the answer is same as that of our shuffle exchange network. If you can recall the shuffle exchange network interconnection pattern, you can figure out that what you had to do there was you had to actually shift or left shift each digit by one position. So say this is your processor in question. So To find the switch or port to which it will be connected, you have to left shift every digit of this binary representation by one position towards its left. So 1. At the rightmost bit you have 1. If you left shift this 1 by 1 bit, you will get 1, then 0, then this leftmost bit will be come in place of the rightmost bit, 0. So this is the destination address for this outward edge from processor, which is address 1. You can see that it has been connected to the input with address 2. This is the input for first stage switches 0, this is 1, and this is 2, and so on. You go like that and construct the entire omega network in this way. Now, last point in omega network. This network is basically a blocking network. So why? Let me explore this with an example. The example itself has been mentioned here. To find the blocking nature, you have to consider a path. Consider the paths from 1 to 6 and 3 to 7. If you consider the path 1 to 6, let me shade it with green color. This is the path from 1 to 6. Say for the time being, processor 1 is making some kind of communication with processor 6. So it is occupying everything onto this green path. That means these switches are blocked by this communication channel. Now, as the definition of blocking and non-blocking network, in non-blocking network, what happens, you see, all the input-output ports which are not occupied at a particular point of time must be able to communicate among themselves for the network to be non-blocking. Now you can see that while processor 1 is making some kind of communication with processor 6, at that time processor 3 and processor 7 are basically free, but they cannot communicate among themselves. Why? Let me make this a red color. To do them communicate among themselves, they have to follow this path. Now, as the path is already occupied by the communication from 1 to 6, processor 3 and 7 cannot use this path. In that sense, this network is a blocking one. Now, let me look at another kind of processor or multi-stage interconnection network called butterfly network. So, it is a bit complicated, or it may seem complicated. So, to realize this thing in a simple way, just I will try to explain every line, synchronizing everything with the example. So, for a butterfly network with P processor nodes, So P is the number of processors into your multiprocessor computer. There need to be P log P base 2 plus 1 number of switching nodes. That means if you have 8 number of processors into your multiprocessor architecture, then total number of switches that you are going to use will be 8 multiplied with log 8 base 2 plus 1. If you simplify this, you will get 8 multiplied with 3 plus 1. That is 32. Now, if you count the number of switches into this interconnection network architecture, you can see that there are 32 switches here. How? Onto row side you have 1, 2, 3, 4 rows, and onto the column side you have 1, 2, 3, 4, 5, 6, 7, 8. 4 rows and 8 columns of switches. In total, 32 number of switches are there into this butterfly network. Now, you see figure 1 shows a network with 8 processor nodes, which implies 32 switching nodes will be there. Now, it represents each node as n rank and column number. That means you can find something new into this representation. It's called rank. It can be thought of as a two-dimensional array or two-dimensional matrix in simple terms. Now, when we represent a particular item into a two-dimensional matrix, we represent it using something like n, I, j, where I is your row number and j is your column index, row index and column index. But in butterfly network, you can see that rather than row index, the concept of rank has been introduced here. Now, if you go through the study material after the tutorial, there might arise one confusion that rank is basically nothing but the row index. So we could have simply implemented this thing using row number along with one number. So why to make things complicated in this way in terms of rank? So it's because rank will tell you the total number of rows into your switching structure. You see, column numbers, that means total number of columns, are actually not arbitrary in case of butterfly network. So you have p number of processors, so you have p number of columns. You have 8 processors into your multiprocessor architecture. So for the two-dimensional matrix structure for the switches, you have 8 number of columns numbered from 0 to 7. Now, how to figure out the number of rows? And the number of rows is basically can be found using this formula. First, you have to calculate the order, which is represented by k for this example, and this order can be calculated by using this formula, which goes like k equals to log n base 2, where n is the total number of processors then k is called the order. So if you go in this way, so to implement the butterfly network for your this structure or for 8 number of processors, your order will be k equals to log 8 base 2 equals to 3. So 3 is the order for our switching structure. Then let me move to rank. If order is k, then ranks will be labeled from 0 to k. Now, from this generalization, try to find the ranks for this particular example. Your order is 3, so ranks will be labeled from 0 to 3. You can see that ranks have been labeled from 0 to 3. So this was the idea behind the rank. Each node into your switching structure can be accessed as n, where n stands for node, rank and column number. For example, now try to understand this thing with the example. The node at column 6, the node at column 6 and rank 1. So here is your rank 1 and here is your column 6 is represented as 1, 6. That means n 1, 6 is your node at rank 1 and column 6. And in the same way, node at column 2, this is your column 2, and rank 0 is represented as 0, 2. Now we have been able to fabricate some kind of definition for the addresses of all the nodes into our butterfly network. Now the last question is how to make connection among the nodes. And here is the connection methodology. And the connection methodology goes like k, your order. So total number of ranks in your structure is k plus 1, that means 4, labeled from 0 to k, that means 0 to 3. Each containing 2 to the power k nodes, that means 2 to the power 3, 8 nodes. 0, 1, 2, 3, 4, 5, 6, 7. Addressed from 0 to 7, that means total number of nodes in each rank is 8. Now let ij denote the node in rank I and column j. For each rank from 0 through k minus 1, connect all nodes ij to nodes I plus 1 j as it has been done into the diagram. So what this line or this step of the algorithm actually says, let me try to define in terms of example. For each rank, say for the time being your rank is 0 through k minus 1. So you have to iterate from 0 to 3 for each rank and connect all nodes ij. So node 0 column 0 should be connected to node I plus 1, that means 0 plus 1 j, which is 0. In this example, you can see that node 0 0 has been connected to node 0 1. Let me do this for another node. So try to find out from this step of algorithm to which node this node with green tick on it is going to be connected if you follow this first step. Give it your thought, try to figure out. The rank of this node with green tick is 1 and its column is, let me count it, 0 1 2 3 4. So 1 4. So you have to connect this node with I plus 1 and jth node, and I plus 1 is 2 and j is 4. So you have to connect node at rank 1 and column 4 with the node at rank 2 column 4. You can see that there is a direct connection between the node with rank 1 and column 4 with the node with rank 2 and column number 4. So this was the exploration for the first step of the algorithm. Now let me explore the second step of this algorithm. So here I can see one mistake into the node. I will correct it later on. Just for now, let's have a look at the example itself. For each rank from 0 to k minus 1, connect each node ij to the node which has rank I plus 1, comma, and column number j plus 2 to the power k minus I minus 1. Here should be a modulo 2 to the power k here, where k is the order of the structure. Now, if we follow this convention, the node with rank I and column number j should be connected to the node which has rank I plus 1 and column number j plus 2 to the power k minus I minus 1 modulo 2 to the power k. So let me try to find the destinations for a processor with this second step of the algorithm. Say we want to find the destination for the node which has rank 0 and column number 0. If you follow this formula, the node to which this particular node should be connected will have rank 1. 0 plus 1, 1. And its column number should be j, that means 0 plus 2 to the power k, that means 3, minus I which was 0 minus 1. Now modulo 2 to the power k, that means 2 to the power 3, and s equals to 2 square, that means 4 modulo 8. If you divide 4 by 8, then the remainder or the result of this modulo division will be 4. So the address of the destination node will have rank 1 and column number 4. You can see in the diagram that node with rank 0 and column number 0 is connected with node which has rank 1 and column number 4, 0, 1, 2, 3, 4. So this was the second step of the algorithm. You can apply, or more precisely I should say you should apply this formula for other nodes as well to get a better understanding of the steps. So this was the tutorial about interconnection network.